In the today's session, we are going to discuss the power factor. So let us start today's session. In the today's session, this session is divided into different sections. In the first section, we are going to introduce our power factor, then the distortion and harmonics, then we are having the introduction to power factors, then power factor, main definition, power factor and true or total power factor, then displacement power factor, and at the last we are going to conclude this. So let us start. Introduction. Power factor, in the very simple words, it is the efficiency of power delivery. Let us assume that we are having this power delivery system. At the input side we are having the input power or generated power, and the output side we are having the output power or consumed power. Consume means useful power, the part of this input power which is useful to do a real work. So if you are going to calculate the efficiency, that means output upon input. So efficiency of this power delivery system is output power upon input power. So that is the power factor of this power delivery system. The part of input power which is useful to do a particular work is called a power factor. So let us discuss how what are these harmonics and distortion. Distortion is an effect of harmonic in our voltage and current waveforms. No, our supply system is AC system, alternating current based systems, and what we are getting from the grid is a AC supply, AC voltage and currents. If there will be a harmonics in our system, harmonics means the reference frequency in our AC system is 50 Hertz. The frequency component other than this 50 Hertz is called harmonics. Such as if we have a frequency component 150 Hertz, so our reference frequency is 50 Hertz, but we are having some content of 150 Hertz in our voltage or current waveform, then it will be considered as a harmonic part. 300 Hertz, more than 300, 400, 500, 550, 1000, 2000, these are some harmonics in our waveform, but the magnitude of these harmonics are very less as compared to the fundamental. In this figure you can see here, this figure is shown here. The green color waveform is your fundamental. This is your fundamental, that means it is a 50 Hertz. In our India, this is 50 Hertz. And these are the some harmonics. In the blue color, this is a blue color waveform. This is our third harmonics. That means fundamental 50 into 3. That means 150 Hertz. 150 Hertz the frequency of this waveform, blue waveform. Then we are having the fifth harmonic is also shown here. This is our fifth harmonic, yellow, fifth harmonics. That means 50 into 5, it is equal to 250 Hertz. That means the frequency of this wave, this harmonic wave, as compared to this green wave fundamental, is the 250. When we are going to superimpose these third harmonic and fifth harmonic in our fundamental, we are going to impose yellow waveform and blue waveform in the green one. That means harmonic waveform into a fundamental. After superimposition, we will get a red color waveform, which is a distorted one. This is the actual waveform what we are getting from the supply. Because there are many loads, non-linear loads like power electronic devices that will inject the harmonic in our supply, and we are getting this kind of waveform, distorted waveform. If harmonics is there, then we will get the distorted waveform, red color waveform. Harmonics means the frequency component other than the fundamental, these are the harmonics, and the effect of harmonics in our fundamental, we will get a distorted waveform. Let's move on the power factor more in detail. Power factor can be analyzed in two different ways. The true power factor or total power factor, and the second one is displacement power factor. In general, the power factor is a true power factor or total power factor when the system waveform is not distorted or the harmonics less. That means in general we are calculating the power factor, and this power factor is nothing but the true power factor or total power factor when the system is not distorted or harmonics less. Then these DPF and true power factor are same. When we are having the harmonics in our waveform, then these two terms true get distinct to each other. So let us discuss more on the power factor. By definition, the power factor is defined as the ratio of useful power to perform the real work, or it is called the active power P, to the power supplied by a utility. The supplied power from the utility is called the apparent power, or S. That means it is a ratio of P to S, or P by S. So this is the actual formula. Power factor is equal to active power divided by apparent power. In this figure you can see here, this is the power triangle. This is the power triangle shown here. This is a power triangle. This is our apparent power. In the blue current line, this is our apparent power. Apparent power is given as equal to the Vrms into Irms. This is our active power. This is our active power, brown color vector. And the angle between these apparent power vector and active power vector, this is our angle phi. And this a green color line, this is our Q vector or reactive power. Reactive power. This is our reactive power, and it is equal to V into I sin phi. It is measured in volt ampere reactive VARS. Apparent power is measured in VA or volt amperes, and the active power measured in watts, VI cos phi. So as we already told you, efficiency of power factor is equal to output upon input. Efficiency is output upon input. So power factor kilowatt upon kVA, that means VI cos phi divided by volt amperes VI. So VI cancelled out, then we will get the cos phi. So in general terms, what we are writing? Power factor. So in general terms, we are writing power factor is equal to cos phi. What is given over here in this slide? This is cos phi. Suppose we are having a system. In the input side power, S power. Output side, the real work is done by the power P. So power factor is equal to P upon S. This is the actual power factor. Now we are going to discuss the total power factor or true power factor. Total power factor or true power factor or power factor, these are the same things. In general, power factor or true power factor is the value that takes into account in the presence of harmonics. If we are considering the effect of harmonics in our waveform, then we are going to calculate the power factor. That means it is a total or true power factor. For a sinusoidal system, it is equal to the displacement. If you are not considering the effect of harmonics, that means the system is totally harmonic free, waveform is not distorted, then these two terms are equal. That means when the system is total harmonics free, totally free from the distortion, then power factor is equal to dPF. Power factor or true power factor is equal to dpf when the system is distorted. Otherwise, these two are a distinct quantity. It is not same. Power actually consumed or utilized in an AC circuit is a true power or active power or real power. So that means active power is also known as true power, also known as a real power, and it is measured in the kilowatts. So active power is what? The power which is actually consumed or utilized in our load circuit or AC circuit. It is called the active power. Active power is also known as true power, also called real power. The unit is kilowatt or megawatt. Apparent power is the total power which is generated by the power plant or a generator or a utility supplied. It is nothing but the product of Vrms into RMS. It is measured in the kVA or MVA. Type of power that does not having real work. It doesn't have any real work. Sometimes it is also called the imaginary power. It is also defined as the power which flows back forth. That means it moves in both the direction in the circuit or react upon it. So react upon it. So that means for a purely inductive circuit, the total power consumed in the circuit is zero. Same thing is applied to the capacitor also. When there is a resistance, then there will be a power dissipation, otherwise no. It is measured in kilovolt amperes reactive, kVAR or MVAR. So this is the real power. This is the reactive power. Power factor can be lagging or leading. So let us take a scenario when the power factor is lagging. I am drawing a vector V vector. Let us assume this is voltage vector V, and this is a load current I vector, yellow vector. So when the current vectors lags behind the voltage by some angle, this is angle phi. So that means in this time the current vector is in direction of clockwise. This is because if this is the reference and we are moving in this side, this is a clockwise direction. Clockwise direction. Our current vector is in clockwise direction, then in this time current lags behind this voltage, and in this time if you are trying to calculate the cos phi, this is a lagging power factor. This is a lagging power factor. When the current vectors lags behind the voltage, then it is a lagging power factor. Again drawing a vector V, and in this time current is leading from this voltage, because now in this time it is in anti-clockwise direction, anti-clockwise direction. So in this time current leads, and the angle between the voltage and current phi, again this is the power factor cos phi, but in this time it is leading. So 0.7 it is lagging. This is just an example. 0.7 power factor can be lagging and 0.7 power factor can be leading also. So lagging and leading. And one case is also there when the power factor is unity power factor. Unity power factor means cos phi is 1. Unity means 1. So that means the angle phi is equal to cos inverse 1. So which is equal to 0. That means in this case, when the power factor is unity, voltage vector V coincide with the current vector, or these two vectors are in parallel. So no angle between the voltage and current vectors. So this is a unity power factor case. Unity power factor case. So power factor measures the percentage of power expended for its intended use or intended application. It may be lagging or leading depending upon the load. So angle between the system voltage and current, and it ranges between the 0 and 1. Low power factor is typically caused by the inductive loads such as motors. In most of the application in the industry side, we are using the induction motor. So majorly our power factor is lagging. Now we are going to discuss the DPF, displacement power factor. What is displacement power factor? DPF is also called a displacement power factor. Displacement power factor is the cosine angle between the fundamental voltage and current. DPF is nothing but the cosine angle between the fundamental voltage and current. In the formula side, DPF can be written as V1I1. V1I1 means fundamental voltage and fundamental current. Fundamental means it is corresponding to 50 Hertz. Because in India, the reference frequency is 50 Hertz. So corresponding to frequency 50 Hertz. So V1I1 cos phi divided by apparent power. Apparent power means V into I. So V1I1 cos phi divided by apparent power or volt amperes. This is a supplied power and this is the fundamental component of voltage and current. So ratio between V1I1 cos phi divided by Vi, this is our DPF. V1 is a phasor voltage of fundamental component of the voltage, and same thing is applied to current side. I1 is a phasor vector of fundamental component of current. So again we are drawing the fundamental component V1. This is a fundamental component of current. The angle between, this is a phi 1. So DPF is nothing but the cos phi 1. DPF is also mitigated with a power factor correction capacitors. In simple words, it can be mitigated with the PFCs, power factor correction capacitors. DPF is most useful for sizing and measuring the effectiveness of power factor correction capacitors, PFCs. Harmonic current do not contribute significantly to the real or reactive components. Both power factor and DPF measures the system frequency. These two terms are equivalent in non-harmonic situations. When the system is totally harmonics free, harmonics less, no distortion, so these two factors are equal. Power factor or total power factor or these two terms are equal. In general, power factor is also called a TPF, true power factor or total power factor. DPF is a good measure of phase shift and power factor correction capacitor performance, PFC performance. Power factor better for overall system efficiency determination in the presence of harmonics. When the DPF and power factor differs numerically, that means there will be a harmonics present in the system. When these two quantities are distinct to each other, that means there will be a harmonics present in the system. This is the measure that the system is having some harmonics. So thank you. This is all about the power factors. Thank you.